Okay, thank you, Ana Maria. So it's a pleasure to be here, and it's nice to have this opportunity to talk to you. So this is the title, Degenerations of Linear Series and Their Moduli. This is a joint work with Omid Amini, who is here. And so in this talk, we're going to see some polytopes, and they're not going to be just restricted to the T-shirt of the speaker. They're going to be there. Okay, so let's briefly recall what we're talking about. Linear series, I mean, they have been introduced here before. These are just spaces of sections of line bundles. So L is the line bundle, and V is the space of sections over any scheme. If you have a nice scheme, and we have other ways of seeing this thing, I will mostly no, we'll just talk about curves here, even though some of the aspects of the work can be generalized to a higher dimension. But over a smooth curve, we can view a linear series as a subvariety of the symmetric product of the curve. Just take the sections and look at where they vanish. So that gives you a projective subvariety. And also, we can associate to it a rational map. Just pick any point and consider the evaluation map. So these are three aspects in which linear series appear, and they are important. So for applications, and so this relation is an important thing. Okay, but what happens is that when the curve is reducible, this is not possible anymore. We can still talk about linear series, of course, but these three ways of seeing things, I mean, it doesn't really work quite well. So I propose a very simple example for us to follow through this. So think of a triangle. So that's our triangle. And let's look at a simple degeneration of, let's look at a pencil of cubics. So here we have our cubics, our cubic. Right? So that's our cubic, and let's look at the pencil. So let's look at a smooth cubic degenerating to the triangle. And let's consider the series on C of t cut out by lines, right? So so cut out by the lines. So, and let's see what happens when t goes to 0 to this linear series. So what happens is the following, is that a general line will intersect my curve in 3 points. Maybe I need to go a bit higher here, but a general line will intersect the curve in 3 points. So that's our linear series on the generic curve. But what about x equals to 0? If I pick the line x equal to 0, the 0 locus is the whole curve, so it's not a divisor. It doesn't live in the symmetric product of the curve. But we can consider this divisor for t different from 0, and it intersects at one of the base points of the pencil. So it intersects into these 3 points here. And they're fixed. As you vary t, they're the same 3 points. So you see that our linear series on, if you view them as divisors on the general cubic of the pencil, they are rationally equivalent. But as you go to the fiber, they become something else. They're not rationally equivalent anymore. So the line intersects in 3 points distributed through the lines of the triangle, but these 3 points are on the same component. So this is the kind of phenomenon that happens for a reducible curve. And if you're just going on to take the closure of, let's say, the set of finite intersections, the 3 red points there in the symmetric product of the curve, we don't get the limit of the spaces of these line sections as t goes to 0. So this set of 3 points here, they're not possibly in the limits of this line here as it degenerates. So you cannot account for them just by taking the closure there. In fact, if you take the closure, you get P2 blown up at 3 points, and that's not the limit of the P2 of line sections as you degenerate from T to T equals to 0. So how to deal with these things? So ideally, if we go back to what we talked about, linear series, ideally, I mean, you want to understand this degeneration in a way that it would be possible to view it in these 3 different ways. So most of the people that have been working on this subject have been trying to generalize what a linear series is. Like Eisenbud and Harris, I'll talk about them in a moment. They considered collections of linear series on the limit curve as a way of understanding degenerations. Or they've been considering the third approach, I mean, maps to projective space. So I have the theory of admissible covariance by Harris and Mumford that replaces these maps by maps from a stable curve to a degeneration of P1, a tree of P1s. And funny enough, I mean, there has been many work on the second approach, which is the only concrete approach that we have. So if you have a curve that degenerates to C, and you look at a linear series as a subscheme of the symmetric product, it will degenerate to something concrete. The degeneration is unique. Right? And what is this, for instance, in this case? OK, so what I've been talking about are these works that by Eisenbud and Harris and Morrison, but in fact, the theory of degenerations as a tool to understand curves in general goes a long way back. The recent interest since the 80s was because of the Brunner theorem. It was Severi that used the degenerations to give a proof, and the actual proof actually came later by Griffiths and Harris. And the work was conceptualized by Eisenbud and Harris with their theory of limit linear series, which I'm going to talk about in a moment. So the Brunner theorem gives you the dimension of the variety of linear series on a curve. It gives you the dimension of that for a general curve, for instance. So as I said, Eisenbud and Harris considered these collections of linear series, which is an approach that can only work for curves of compact type, curves whose generalized Jacobian are compact. But before that, as I mentioned, Harris and Mumford used these admissible covariance to understand and actually to prove that MG is of general type for odd genus, high enough, above 20-something. And Eisenbud and Harris used their theory to handle the remaining case. So that's to talk about some applications of that. The 2 theories are the only 2 that are established in the sense that people have known them for a long time, people have applied them, and, but they are far from covering all cases. I mean, admissible covariance are a linear series of rank 1, and Eisenbud and Harris are just for special types of curves, curves of compact type. And even when they intersect, when you can talk about the 2, they're not quite equivalent. There is a sort of translation between them, but it's not quite the same. So the problem that we interested in is this. I mean, what Eisenbud and Harris, they call for a more comprehensive approach in the late 90s. So linear series are spaces of sections of line bundles, right? So we may start by understanding how line bundles degenerate. And I mean, here you have a large theory. So it started with the Indian mathematician, de Souza, who constructed it for irreducible curves. There is Altman and Kleiman for families of curves, Onda Seshadri for reducible curves, Caporazzo for the construction of a compactification of the Picard scheme over the moduli of stable curves. And a lot of people have worked on these. I put some younger names there. Mello, Viviani, Pacini, Abreu, there's Cassim, Pagani, and so forth. So the generations of line bundles to a curve, we can view them as either line bundles on a semi-stable mode of the curve, or as these torsion Fourier equation sheaves on the curve itself. And that's how we're going to view them anyway, the second approach. So if you have, so what's this, a torsion Fourier equation sheaf? It can be described as a line bundle tensored with the ideal sheaf of a finite subscheme. So if your curve is smooth, then this sheaf of ideals is a line bundle as well, so that's a line bundle. In general, you can have this presentation of the sheaf, which is not unique, but it sort of tells you what's going on. So these are the sheaves that, that we can try to parameterize in a compact variety. So I'm going to talk a little about them. And the thing is that when you have a degeneration of a curve like that to a reducible curve, the thing is that there are infinitely many limits for this, for the line bundles. So we say that the relative Jacobian is non-separated. So, and we've seen this in this case, right? I mean, because these correspond to different line bundles, the red and the yellow divisor here. So how to handle this? I mean, if there are infinitely many limits, what can we do? Well, we can do as it has been done for vector bundles on smooth curves. We can introduce a stability notion. So I'm going to talk about these stability notions that people use. So let's start with this nodal projective connected curve. I'll introduce some notation now. So we have the set of irreducible components, which we call V. We're going to introduce the dual graph of the curve now. So for each element, you have a corresponding irreducible component. You have the nodes of C, which we will view it as an edge set. So the nodes are the normal crossings, the singularities that we have, the only ones that we have. And then there is the associated dual graph, because to every edge, we're going to have an edge between two vertices corresponding to every point of intersection between the components. So that's the dual graph of the curve. So there is some combinatorics, of course, here, and it's encoded in this dual graph. So given a subset of irreducible components, we can consider their union. It's a subcurve. And what we can do is you can try to compute the multi-degree of, or the degree of your sheaf on that curve. So what you see here is there's this first part. If it was just a line bundle or sheaf, then we're just summing up the multi-degrees on each of the components inside C of S. But there is a correction here if you have this divisor here. So I'm defining this function here on subsets of V that associate sort of the degree of the sheaf on that subcurve, which is this part here. And then there is a correction term here that doesn't depend on the sheaf itself. These are just the points of intersection of that subcurve with the complementary subcurve over 2. Oh, sorry? F is the finite set on the curve, right? So another way of viewing this is you pick a sheaf L, restrict to the subcurve, and remove torsion. That would give the degree as well. So it's not really dependent on F. It's something invariant. Any more questions? So we can pick an element. So that's a function that we obtain in the power set of V, and we can have another function if we pick a tuple, just a function from V to sets. Yeah, so just a function from V to R. This is the real field here. I'm sorry, it doesn't appear. And then you have you can define also Q on subsets. So the idea here is that we view this Q as a sort of virtual multi-degree, right? It could correspond to a multi-degree of a line bundle, which is the top of degrees on each component. And there up above, you have this, without this correction term, the degree of the multi-degree of the sheaf. And the condition is of Q semi-stability is this, that mu of L, this function is always greater or equal than Q, but we need an equality there as well. So this is, if you have seen people talk about this, maybe it's a different way of putting things. What you have to think about this in this way is that we're sort of describing what's that? It's a lower bound, right? So mu of L cannot be very far from Q. So basically, if you fix Q and you look at L's that satisfy this, what we're saying is that the multi-degree of L cannot be very far from this virtual multi-degree. It looks like that there is just upper inequalities like that, but once you impose this equality here, you have inequalities the other way around as well. So it gives you some, and the distance between these multi-degrees is encoded in this correction term here.
Here in the definition, there are two different Q's, right? Kind of confusing.
Yeah, so that's because we abuse the notation here. So given Q, I denote by Q the same, by the same Q another thing. Right? So Q can be regarded as a function from V to R, but also a function of the parts of V defined in this way. In here, I'm thinking of it as the functions on the parts of U. Q of U is this definition here. So it's the sum of the Q's. So that's the total degree of Q compared to the total degree of L. In this case, the total degree of L is the degree of M minus the number of points in F. So this is really telling you that if you want to view it that way, that the multi-degree of the sheaf is close to this virtual multi-degree that you get. I mean, there might not be a line bundle which has degree multi-degree Q because Q takes real values. But if there were, what we're saying that the multi-degree of these sheaves are close. Yes, so it appeared in distinct ways. I mean, it appeared in the work by Oda and Seshadri. It appeared in the work by Caporazzo. She called this basic inequality. And it really came from stability conditions when she was trying to construct this space. So the idea here is that you see, I mean, this mu of L, you can think of that as a degree of a quotient of L. Right? When you restrict your L to the subcurve, and model out by torsion, what we're really saying is that this degree should be bigger than something, which is, sounds similar to the condition of stability on vector bundles that you require that a quotient of the vector bundle should have a slope bigger than the slope of the bundle itself. Here, there is no canonical way of, in fact, there is. I'm going to talk about that. But there is not a single notion of stability. There are several notions of stability, and that depends on Q. On the other hand, it's everything discrete. Right? In case of vector bundles, you have to pick any quotient bundle. There could be a moduli there. And here, no, everything is discrete. Any more questions? So what's this Q, right? Well, this Q is a choice that you make. So for instance, if I'm interested in the divisors cut out by lines here, then I can look at O of 1. That's 1, 1, 1 stable. Easy to see because that's actually the multi-degree of the divisor cut out by the lines. But it's not 3, 0, 0 stable. Right? It's too far, 3, 0, 0 from 1, 1 with respect to the points of intersection of subcurves there. On the other hand, if you're interested in this divisor there, the yellow one, you're going to look at this 3, 0, 0, which is the multi-degree of D, and it's semi-stable, or actually stable, but not 1, 1, 1 stable. So basically, what I'm saying here is that if you choose your polarization, you're basically restricting yourself to some set of limits rather than others. Now, are there natural stability conditions? So I just came up with this Q out of nowhere. Are there canonical ones? Yes, there are. These are those that Lucia used in Caporazzo. She considered this for curves of genus greater than 2, equal than 2, she considers this virtual multi-degree, which is the degree of the canonical rescaled so that it has total degree D. Right? And then we can talk about stability for sheaves of degree D using this Q. Right? So this is canonical in the sense that if you're in the moduli and your curves degenerate, you gain some components by breaking up some reducible components, that behaves well. But if you're interested in these yellow divisors there, I mean, this doesn't work here. Of course, this wouldn't work here because this is genus 1, but the canonical polarization here would be exactly the polarization, or the Q would be 1, 1, 1. And the reason here is that, and that's the reason why only this polarization works in moduli, is that, I mean, Cass and Pagani, I mean, they sort of describe this well. It's that things can change, right? So for instance, in this case, the triangle here, I can have a family of triangles such that suddenly YZX becomes XYZ. Right? So if you assign your degree, let's say, of Q to be equal to 3 on X, as you move around, X will become Y. And then what do? I mean, you didn't assign degree 3 to Y, just 0. So if you want to think of in terms of moduli, the only polarization that works here is 1, 1, 1. And that's an issue, because we need to consider several limits. Part of the description of what's happening with divisors here is happening for other semi-stability conditions. Any questions here? So that's what I said. How do we explain this limit divisor? Just by looking at line sections. Right? As I said, if you look at the line sections and take the closure of that, you're not going to get this divisor. So for instance, where do the flexes go? On a cubic, you have 9 flexes, 9 inflection points. And on the triangle, you don't see them. It's flat. OK, so what Eisenbahn and Harris proposed is that to consider not one limit line bundle, but several, one for every component of C with the appropriate multi-degree. So in this case, they would consider the line bundle 300, for instance. And for curves of compact type, that worked, because limits can be chosen to be line bundles with assigned multi-degree. But if your curve is not of compact type, you cannot really establish that, OK, I want to look at the divisors that have degree D000. No, that won't work. And how to do it more generally. So here comes the work that I've been doing with Omid. We started working on that, and suddenly we realized that we're just having a different take on, OK, I need to talk about the work by Osserman before. That's good. So Osserman observed that this approach by Eisenbahn and Harris was not really very functorial, and what he proposed is to consider all limit line bundles of effective multi-degree. So that way you would consider all divisors that happens, and he proposed that for a one-parameter family of smooth curves, degenerating to just a curve like that. So his first approach was for curves that have 2 components intersect at a node. Then he generalized that, but it became a lot more messier for one-parameter families with Renan Santos and Eduardo Vital, ex-students of IMPA. We used equivalent representations to organize this degeneration data. But we were restricted by this condition that the total space of the family is smooth. And that's what I started beginning to talk about. This is an old idea, maybe not so old, but the idea by Kapranov in a new way applied to linear series. So that was an interesting development in the early 90s by Kapranov. And let me tell you more or less what he did. And then I'll say how it applies to us here. So Kapranov considered this a finite collection of finite dimensional vector spaces and the union and the action by the torus on the Grassmannian. So the torus actually gives you automorphisms of U, which are multiplication by constants on each summand, different constants. Right? And then you can use that to send any vector space, subspace, to another one. So let's look at the Grassmannian of R plus 1 subspaces of U. If you have a general point on W, then the projections to the partial sums, will have maximal rank, which means injective or surjective, depending on the conditions there. And what he did was to consider what he called the Chow quotient of G. So you take, let's see, where am I? Oh, okay, pressed the wrong button. So he considered the orbits of a general W, the closure of the orbit, that's an irreducible subvariety. You look at the prime cycle associated to it. It's a point on the Chow variety that parameterizes exactly cycles. And we consider all these points and take the closure. That's a projective subvariety of the Chow variety, which he called a Chow quotient. And in fact, it's a sort of a quotient, right? Because you're parameterizing the orbits of these general objects, right? And some compactification of that. So to be precise, that's not what Kapranov did. He worked with the case just that the dimension of U of V is equal to 1. So that's the maximal torus acting on the Grassmannian. Lafort considers something which is more useful to us, where the dimensions of the UV are R plus 1. So that means that our subspace, if it has maximal rank, you have isomorphism to UV. So that's a compactification of PGLR, R plus 1, in a sense. And the general setup was considered by Jean Syracuse and Wu, which is the setup that I mentioned, where the spaces have variable dimensions, not just the same. And they go along and they describe the boundary cycles. So the boundary cycles, they are reduced sums. So there are no multiplicities here. And the prime cycles that you have there, they're orbits also, but of certain subspaces which are not general. So these are orbit closures. And the condition that these subspaces must satisfy is that they're associated polytopes. They must form a polyhedral decomposition of the polytope associated to a general W. So here the polytopes come up. So what are these polytopes? So Kapranov and Jean Syracuse and Wu obtained the polytope in a different way, in 2 steps. They first associate a matroid to that, or a matroid on a multiset. And then out of the matroid, they considered certain vertices, integral vertices, and the convex hull. We do it directly. What we do is the following. We consider this mu of W. It's a function on the subsets of V that associate to every S the dimension of the projection to that partial sum. Dimension as a vector space. Dimension of a vector space. And then they define the polytope. I mean, we define the polytope, but it's the same as the one before, as the set of real valued functions, Q in RV, that satisfy this condition. That Q is, for every subset, is smaller or equal than this mu of W, And for large Q, I mean, for the whole set V, you have that Q of V is the dimension of W, which is R plus 1 in our case. Right? So this polytope sits in a hyperplane. It sits in the hyperplane given by QV is equal to R plus 1. So it's similar to the conditions that we use to define stability. And that's why, I mean, I insisted on having that function mu for L, for a torsion-free sheaf. And we can look back now and define another polytope, this time associated with our sheaf, which are the set of Qs such that L is Q semi-stable. So we're looking the other way around. Instead of fixing Q and try to work just with the sheaves that satisfy the stability condition, we look at the sheaf and ask when it's going to be Q semi-stable. And that happens for Q in this polytope there. So I've been calling this the semi-stability polytope of L. So I have these two polytopes. They're given by these functions mu. What do they have in common? So the answer is that these functions, they are submodular functions. The mu of L and the mu of W, they are submodular in the sense, well, there is this extra condition that mu of the empty set is 0, but they satisfy these inequalities for every subset. That's called submodularity. So it's, if you can, I mean, it's clear that these inequalities hold for vector spaces. Very easy to show. And they hold for the sheaves as well because of that extra sum that I put in the definition of mu L. It wouldn't have worked otherwise. Okay, so these functions are submodular, and there is a theory that describes polytopes associated to submodular functions. And so this is known as the base polytope of the polymetroid associated to mu. So a polymetroid is a polytope, and it's the polytope that is given by these inequalities here. And if you let Q of V equals to mu of V, that's the base polytope of the polymetroid. So there is a lot of literature on these polytopes. I mean, we can understand their faces in terms of other submodular functions and a bunch of things. And our reference for that has been a book in combinatorial optimization. So that appears in other areas as well. So what we do now then, I mean, we're considering linear series, we're considering the limits, which would consist of limit sheaves, but also the limits of the spaces of sections. And what we can do is, just as Kapranov did, we can consider the collection of all these limits of linear series of a linear series on the generic fiber. So now we're considering a family just like this space of cubics, degenerated to a nodal projective curve. The dual graph is fixed. And then we think of a linear series of degree D and rank R degenerating to the special curve. Right? And then you have this collection of all limits of linear series. How many are there? Well, we're going to talk about that. But the idea is that we pick all this data and organize it in the following way. So you can look at the subspaces of sections here, of Li, of the sheaf, right? Your sheaf, you can look at the restrictions of the components. That's what this LIV is the restriction of Li to the components, mod torsion. And then you have this sum here. So here is a space which is decomposed as in Kapranov's. Right? So I can associate to this the polytope associated to W. So that's how the polytope appears. And then we can pick, okay, we have two polytopes, the one associated to L, the one associated to W, and we can pick a sum of them, a linear combination of them. So that's the theorem. is that if you just concentrated on the polytopes associated to the sheaves, you get a polyhedral decomposition of this hyperplane of RV given by this condition that Q of V is equal to D, the degrees of the Li. And also, if you look at the polytopes associated to the WIs, so the vector spaces, they form a polyhedral decomposition of this simplex here. Right? So this is the set of positive Qs, total sum R plus 1. But you can combine all of them, like in here. These are positive guys, so this is a submodular function. We can look at the polytope associated to this, which is just the linear combination of the polytopes associated to Li and Wi. And you can still get a polyhedral decomposition. But now the total value depends on alpha and beta. So let me show you some pictures to show what are the shapes of these polytopes. So in the pictures, we'll basically be talking about this curve here, the triangle. So it has 3 components. So I'll be looking at RV, so that's R3. But since the sum is fixed, I'm going to project into the first components. So what you're going to see is a planar description of this polyhedral decomposition. So these are the polytopes, the semi-stability polytopes associated to the limits when, exactly in this case, if I'm picking a general cubic here, where the total space is regular, is smooth, then you get that all the polytopes are the polytopes, stability polytopes for invertible sheaves, for line bundles, and they have all the same shape. It can be more interesting if you allow your total space to be degenerate. Then you can have 4 types of full-dimensional polytopes. There are those correspond to line bundles, but also those that correspond to sheaves that fail to be inverted but just one of the nodes. And by the way, you might be looking, as I do often, to the full-dimensional polytopes, but each small polytope, a segment, a vertex, all of them correspond to invertible limits, not to invertible limits, but to limits, torsion-free limits. So this is the case where you have rates of approach in your degeneration given by 5, 3, and 2. You don't need to restrict to integers. So this is the case where we made rates of approach irrational. So there is a 2 pi here. Right? And then you get something more complex. So this is the case for line bundles. This is the it spreads out, right? It doesn't stop there. It spreads out to cover the whole plane. This is the vector spaces. So this is the polyhedral decomposition of the vector space that you get in this problem here. So basically, since for vector spaces, we're talking about a polyhedral decomposition of a simplex. So you get finitely many polytopes in this way. So this 1, 1, 1 is the polytope associated to the system of lines that degenerate to the system of lines. But also you have the polytopes associated to these other degenerations that gives you the 3 points on one of the components. And there are 3 components. So that's the polytope decomposition of the vector spaces. We're going to come back to this picture there. But we have a few more pictures, and I was a bit lazy, didn't produce the pictures for this special case. But for a case where you have, instead of the depth of lines, we picked a certain pencil of conics, right? Degenerating to our triangle, still always our triangle. And then, we have, don't look at the small triangles there, but that's the polytope decomposition of the large triangle, right? It's also 4 polytopes there, and these are the polytopes. And we can put together what we have for the sheaves and what we have for the polytopes and do a linear combination, sort of. And that's the polytopes that we get. So the colors are just for seeing them better. What you can try to view is this as a sum of the polytopes that appeared here, these triangles, and the hexagons that appeared in the first picture that I showed you. So the shape of these depends on alpha and beta, but not the combinatorics of it. So if you have two polytopes that intersect in a codimension one phase, for a certain alpha and beta, they will intersect for other alpha and beta. Right? So it's just... Okay, so these are the kind of pictures that we get, and they are not just beautiful. I mean, they give you information about the linear series as well. So let's see what I have in the next slide. Maybe I should go back. Yeah, so let me go back to this. So for instance, no more pictures? Ah, right, yeah, you see why. This is just a joke. Good to get jokes, huh? Just a few seconds. Okay, so what I'm going to say is that, I mean, to each of these polytopes, okay, press the wrong button, to each of these polytopes here, the full dimension ones and also those of a smaller dimension, there is associated a limit linear series. Right? And what's interesting here is that if you look at the linear series associated with the maximal dimensional polytopes, like for instance this red one here and the blue one here, they share a facet. And if you look at the maps between these two linear series, the one here and the one there, either there are no maps or it's a one-dimensional space. So there are maps between these linear series, or maps between sheaves that take the sections of one linear series to the other. And in this case, if the polytopes, they share a facet, that map, if non-zero, if there is a non-zero map, it's unique, modulo multiplication by constant. So the polytope decompositions tell you also about what you're handling, about the linear series. So this is one of the things that we did. And just recently, Omid was here for a month before ELGA, and we did some more work. So here, basically, I was trying to convey the idea, and I will go back to this example here, that if you know well what the degeneration data are, then you can actually describe what these limits are, and you can characterize them and know them well. But it's also possible sometimes to know what the limit data is if you know well what the degenerating data is not or are not. Right? So this is a joke, actually. So, but what I want to claim, that's our second approach. So second result that I'm going to say here today is that we are able to describe all the limit of the generating canonical series when the nodes of C are in general position. Right? So out of the special positions, so that's why I'm saying if you know what they're not special, they are general, then you can describe the canonical series. So to every smooth curve, there is a canonical linear series, the differentials and all of them, and then you can try to describe what happens when the nodes, when it degenerates to a curve like that. And I'll talk a little more about this. So we use the fact that C is general for the given dual graph. So we're going to fix and the genera. So I'm going to fix that. What I'm going to assume is that the points on the components are in general position with respect to the canonical on that component. We use meromorphic differentials. So you can view the space of sections of the canonical as a space of meromorphic differentials, so tuples of differentials on each component. Using this notion is due to Rosenlicht, the regular differentials. So these are meromorphic differentials that at the branches over the node, the sum of the residues are 0. So that's Rosenlicht condition. So we view each limit, not just that limit. Of course, if you look at the canonical series, it's a limit of the canonical series, but it's not the only one. But we can view each of them, each of the limits inside omega. So we're going to view these sections as tuples of meromorphic differentials. Here is something very important that we use. So these 5 authors, they describe the conditions that these limit differentials must satisfy. Of course, they involve Rosen-Licht type conditions. There is the residual theorem. The sum of the residuals must be 0. But then there are extra conditions called global residual conditions. And those were crucial for us. And what we do is we describe the limits of all these Wi inside omega. So for each degenerating family, you have a collection of Wi's, right? And we describe all of them whose associated polytope, in the sense of Kapranov, is full dimensional. And from that, we get all possible limits. And we went further. That's what we did in the last month. We parameterize the collections of these linear series that arise from all degenerations of the curve. So we don't fix one degeneration, we consider all degenerations. For each degeneration, there's going to be a collection of these Wi's. We put all of them together in a certain scheme, which is projective. It's all the limits are there, so it's projective. And it's described through a certain fan. It's not a toric variety because you have to consider some construction of the fan. It's a dual thing. So in fact, this projective scheme is a union of, well, we believe projective varieties. I mean, there are some details that we haven't really worked out fully. But that's to say that we can actually describe all limits of the canonical systems in this situation, which is an important system to work on. So how much time do I have? Oh, almost there. Good. Questions here? Okay. So I'm almost there. So I'm going to talk about maps. So I started talking about these 3 different ways that you can view your a linear series on a smooth curve. And also here, there are 3 different ways that we can try to understand these linear series that we're parameterizing. So they're important because they describe maps. Let's look at maps then. So we can consider this quiver associated to the polytope decomposition and its representation by linear series. So let me just draw here some polytope decomposition. Maybe just. So what I was saying is that to each polytope, you have associated a linear series. Right? So that you have a Wj, Lj. Right? And you can look at the quiver associated to the polytope. So what's this quiver? You look at these polytopes, which are maximal dimensional, and you put a vertex here. You look at the facets between these polytopes, and you put 2 arrows here, going back and forth. And then you have a representation of this quiver in the category of linear series because you have for each point a linear series. But you also have a map. We can show that in a limit situation, there is a non-zero map here. And this map is unique, modular multiplication by constant. So you don't need to give the maps. The maps are there. Right? And then you have this representation. It's a representation of vector spaces. But these vector spaces are also vector spaces of sections of the line bundles. So you have 2 different types of representation here. And we're putting this together with the linear series. And what we do with these representations, we can do a lot of things. We can look at divisors. So you can look at the Wj's, and you look at the sub-representations of dimension 1 of these Wj's. So they correspond to compatible sections of all these line bundles. If you look at their common zeros, we get divisors. So that's the way to get divisors associated to this linear series. And we can use the evaluation maps. Right? So if you have a linear series, that's how you get the maps, right? You take the evaluation maps, and by doing that, in the equivalent representation, the W, we get a one-dimensional sub-representation of the dual representation. Just take the dual of the vector spaces, and you have, not for every point, of course, but for a general point, we get. So we get then a rational map to this LP of W star. This is our notation for linked projective space, which is the variety parameterizing subrepresentations of dimension 1 of our representation. Right? So that's a quiver Grassmannian. And so I can tell you what happens in this case of degenerating the pencil of cubics. What happens is that what's the map that you obtain in this way? Well, it's not a rational map. It's defined everywhere. And that's the picture. So this LPW star, it has 4 components. One of the components is P2. The other components are P2 blown up at a point, the Hitzebrook surface. We pick these exceptional divisors, and we put them together by identifying with the lines of the triangles. Right? And if you look at the map that I just said there, this map actually sends the curve to this. This is the red. The red part here is where the curve lies inside. That's the image. So if you were to focus on just what Eisenberg Harris do, I mean, they look at the linear series which have maximal degrees on the component, you wouldn't see the base P2 here. You would consider a map to the union of these Hitzebrook surfaces. But then that union is not. The -1 curves, so you get a ruled surface, right, with the Hitzebrook surface. So the -1s are here. We put it together here. And then it's funny because you also see the triangle there. So if you follow along these lines, the rules, and you have a map from all this setup here to the P2, which is just a projection along these rules. And then you get the triangle. So it's as if we are just looking at our triangle in the plane, and we didn't see this nice geometry that you had on this surface there. So if you want to look at the flexes, I talked about them, then you have to look at how this curve here flexes on these F1s. Then you'll be able to tell where the flexes go, for instance. So that's to say that we can actually describe these things. When you know the data well, in case of plane curves, you can actually describe what's going on. And I finish here.